Hello everyone, welcome to the first video I'm going to be posting on my channel. This first video is going to be about coroutines and how to use them in the Roblox engine. Alright, so to start, I just want to review what most people think of when they think of how code is ran. So, normally, scripts are read from top to bottom, or starting from line 1 and going to the last line. So we do a basic example here. I'm going to print out 1, print out 2, print out 3. And I'm using warn here just so it shows a little more in the output window. And it's just a personal preference for me. So if I go ahead and run this. 1, 2, 3, as expected. Now, coroutines can work in this way, but sometimes they behave a little differently. So I actually made some diagrams that we can look at. So the example I showed and how most people think of how code executes is in what is known as serial mode, or it's also called synchronous, alternatively. So this diagram is showing 3 different instructions. You can think of them as instructions, sub-processes, tasks, jobs, whatever you want. But there's 3 sub-processes that are being executed. The leftmost point in this diagram is the starting time, and the rightmost point is the ending time. So you can see that the first task is running, the second task is running, the third task is running, and they're all running one after another. So the first task runs and finishes before the second task runs, and then the second task runs and finishes before the third task runs, and so on. And that's exactly what this example right here is showing. It's outputting 1, then it's outputting 2, and then it's outputting 3. So that's the intuitive way to think about how code execution works. But with coroutines, it is a little bit different. So just for an example, let's say you want to make a HTTP request to some external server somewhere on the internet, and let's say that the first task is in charge of doing that. And let's say that this external server unfortunately takes a while to respond. So let's say it takes like 10 seconds to respond for this specific request. So task 1 is going to start. It's going to prepare the message. It's going to send the message. It's going to pause. It's not going to do anything for 10 seconds because it's awaiting a response. And then it's going to receive the response. And then it's going to continue and then finish eventually. And then it's going to run the other tasks. Now, this is fine unless you don't want it to be fine. So, because, for example, what if the second task and the third task don't care what the response from the first task is? Then it's just essentially wasted time that's happening. So that's where coroutines come into play. And I will show the coroutine diagram now. So coroutines run in what's called a concurrent mode. So generally there'll be some manager that's managing all of the coroutines or sub-processes, essentially. So back to the example of the HTTP request, the first task, back to the example where the HTTP request, where the second and third tasks don't depend on what the response is. It's going to it's going to start the first task, and then it prepares the message. So that's maybe this little block right here, this first leftmost block. And then it's going to send the response to the external server, and it's going to await a response. But since the second and third tasks don't care what that response is, the first task is going to tell the manager, which is managing all of the coroutines, hey, I'm yielding, and the manager is going to say, all right, well, I can resume another thread or subprocess that is ready to run since you're yielding, or since you're awaiting, like yield, suspended, not doing anything. So it's going to start running the second task, and then the second task runs and finishes, the third task runs and finishes, and then after that, after 10 seconds approximately of waiting, it's going to resume the first task, and it's going to run and finish the first task. And that's what coroutines allow you to do. So there's no time wasted in this specific example. And some people confuse concurrency or coroutines with parallel processing, and just to differentiate them, a parallel system or processes is going to look like this, where you have the first task, the second task, and the third task, and they're all running at the same time. So in the concurrent example, all of these tasks aren't running at the same time. They're just kind of fragmented across the timeline. So you can think of the serial example, and you're just kind of fragmenting some of the tasks to different points in the timeline. But with the parallel processing, you're actually running all of the tasks at the same time. And this is done on multiple processors, whereas the concurrent system is all like on the same process. So I'm going to go back into Roblox Studio, and we're going to work some examples. So the first step is understanding how to create a new coroutine. And there's actually two ways nowadays, using classically the coroutine library, but there's also the task library nowadays. So I'm going to start with the coroutine library, and how we create a new coroutine or thread of execution, of course all under the same processor, is we're going to use the coroutine.create function. It takes a function as a first argument, and I'm just going to pass an anonymous function. You could also define a function beforehand and pass the reference as the first argument. But for this example, I'm just going to do this. Inside of this function, I'm going to type process ran. And now this is only actually creating the coroutine. It's not starting the execution of the coroutine. So how we do that is we use the return value of create, which is a reference to the thread that it's going to be ran inside of. And then we can go ahead and call coroutine.resume. The first argument is a thread. We're going to pass that reference in. Now if we run this, you can see that it says process ran. And you can also use a function called running under the coroutine library to print out a string version of the address that the function is running inside of. So if we run the simulation, it's going to print out process ran, and then thread, and then just some address, which doesn't matter. So that's pretty cool. But I also want to make the point that right now this code is still running in serial or synchronously. And we can prove that by adding a print up here. So I'll say script starts. And then after the resume, I'm going to say script done. And if we run this, it's going to print out script starts, process ran, the thread reference, or sorry, the thread address, and then script done. And if we look at the code, that's the exact order that we called the output or the warns in. So script starts, process ran, thread, and then script done. So this code is still running in serial, and that's because there's no yields inside of this new coroutine. If we were to put, and I'm going to use a function under the task library called task.wait, where it takes a first argument of the number of seconds to wait. If I intentionally yield for 1 second, and I go ahead and run this again, it's actually going to print script starts, script done, and then after 1 second, it prints process ran and then the thread. So that's kind of what the concurrent example is showing. Although we only have really one task, or technically we have 2 tasks running right now, but you can see that this code is running concurrently. Another important note, another important thing to go over is, I'm just going to go ahead and delete some of these real quick. Comment these out. A coroutine can only be ran 1 time. So once the execution reaches after the final line or the final instruction inside the function body, the coroutine has finished execution and can no longer be ran again. And I can prove that by trying to call coroutine.resume on the thread again. So if I run this, you can see it only prints out process ran, and it only does what's in the function body 1 time, and then subsequent calls to coroutine.resume don't do anything. So here's another point where we can bring up another function called coroutine.status. So each coroutine has its own status. So if I do status, and then it takes a thread as the first argument. Thread. So the order of execution for this is we create a new coroutine, it's going to resume it, and it's going to run in serial because we don't have any yields. And then we're going to print the status of the thread after it's finished running. So if I run this, you can see it does the function body, and then this print right here prints dead because we've finished the execution of this coroutine. And there's actually 4, including dead, statuses that you can that a coroutine can have. That includes normal, running, suspended, dead. So normal is when you create a coroutine but you haven't started the execution of it yet. Running would be during the execution. So if I were to print coroutine.status with the thread reference or coroutine.running inside of this function, it would print out running. And then if I were to have like a task.wait inside of here and I tried printing this out right here, it would print suspended. And then of course we got dead for this example because it finished running. So, alright, so I'm just gonna clean up some of this a little bit. And I'll just print out the thread address for now. So the next function I want to talk about is coroutine.yield. So I'm actually going to call it inside the function body, and it doesn't take the thread reference as an argument because the thing that's running this code knows that you're calling this inside of the function body of the new coroutine. So you don't have to pass the thread reference to coroutine.yield. And what this function does is it's kind of like task.wait, except you don't have to pass the amount of seconds it has to wait for. You're just basically saying you're telling the coroutine manager, hey, I want to yield this new coroutine, but I don't care how long it yields for. I just want to yield it. And so if I try to run this, it's not going to print anything, because we started the execution with this call to resume, and then the first instruction is to immediately yield. And let me just add a script done down here. So you can see that script done prints out, but this new coroutine is essentially going to yield forever because there's no other call to resume it. And so let's actually do that. I'm literally just going to call coroutine.resume thread again. So the first call to resume is going to start the execution. It immediately yields. And then the next call is going to resume this yield right here. So we run this. It's going to print out the thread address and then script on. So this is running in serial as well. And another important idea is we can actually pass data into this function through the resume calls. So I'm going to go ahead and comment out the yield for a second. I'm actually going to add a parameter to this function right here. I'm just going to name it x for the example. And I'll just warn the x, whatever this value is. And for the initial resume, I'm just going to pass a second argument, and I'm going to pass just, let's say, 7. So if I run this, you can see that 7 gets printed out because I am, whatever you pass after the first argument and resume, it's going to get passed as a parameter to the function if you're starting the execution. And you can also, if I had this coroutine.yield right here, and we had this other resume, you can also pass data to this, but whatever you pass after the first argument for resuming a thread in this fashion is going to it's going to make these arguments the return values of this coroutine.yield call. So I could say local y is equal to that, and then maybe we'll warn the multiplication of x and y. So this should print out 21, which it does. So yeah, it's pretty cool. So yeah. And just to prove my point one more time, we can create multiple threads. I'll say thread 1. Thread 2, thread 3. So I just made 3 coroutines and I resumed each one of them. And if I run this, it's going to print 3 different threads. So they're all running in separate threads, but in this example they are running in serial because there's no yields in any of the function bodies. If I were to add like a yield to the second thread, I messed up, wait, maybe 1 second. I'll go ahead and print out a number associated with each as well. Then you can see it runs the first thread, no yields, so it's gonna run this code in serial. And then it runs the second, but there's a yield, so it tells the manager of the coroutines, hey, I'm yielding. So, and then it starts another thread. And then we'd run the third one, no yields, it's gonna run it. And then after 1 second, it's gonna resume, and the second thread is gonna run. And that's exactly what we see in the output. And they're still all running in separate threads. Alright. So now I'm just going to go into the task library a little bit. So the task library is relatively new. I mean, it's been around for a while now, but alright, yeah, so here we go. So the way you create, there's actually multiple ways you can create coroutines with the task library, but they're a little bit different. So the first one is with task.spawn, which is a function. And the first argument can take a function or a thread. If you pass a function, it's gonna create a new coroutine and run that coroutine immediately. And if you pass a thread, it's gonna resume the coroutine if it's suspended. So for now, I'm just going to pass a function, and we're going to print out just 1, for example. Change up running as well. So just to prove my point, we don't have to do any coroutine.resumes. It just immediately runs it. And this behaves the same where you can't resume like a coroutine after it's already finished. So if we try, so here's actually an example. So you can pass a thread to the first argument of task.spawn. So if we try to run this, it's not going to work. It's only going to print the one time it's executed because it's already finished executing. And of course, we can yield inside of here. Let's say script starts. Script done. Delete that. And you can see it functions the exact same as our examples with the coroutine library. So this code is running concurrently to the thread that the script is running inside of. Now, there's also, so I mentioned there's actually multiple ways to create and run coroutines in the task library. Another way is with task.defer. And task.defer can also take a function or a thread as the first argument. If it takes a function, it's going to create and resume a coroutine. And if it takes a thread, it's just going to resume the thread you pass it. So for now, I'll just pass a function, and I'll just print process runs. Now, there is a difference between task.spawn and task.defer. And I'm actually going to highlight that by using test.spawn in this example. So let's say you call task.defer first, and you call task.spawn second. So I'll print out spawn and defer. So if I run this, you can see that I called this defer first, and then I called spawn second, but spawn gets printed out first and defer gets printed out second. And I'd like to show you this using more diagrams. Okay, so I'm going to hide this. Alright, so I pulled this image off of the Roblox documentation, and I want to talk about how Roblox runs. So during a simulation or during a game, the stuff that you're seeing and like everything that's happening with the game is running on a per frame basis. And what this image is showing is everything that happens in a single frame. And a frame is really just some interval of time where a bunch of computations happen. So for example, if we look at this image, you can see at the start or at the top we have user input, where input events are handled, mouse movements, gamepad, and then next we have rendering. So some stuff happens, the pixels are drawn to your screen, and then we have some different stuff like receive jobs. We have garbage collection, which is a whole other thing. We have the simulation job, which is basically like physics and some legacy features. And then we have heartbeat at the end and some other stuff. So these are really just labels for processes that are happening all in the same frame or interval of time, which frames happen really fast. The Roblox games are capped at 60 frames per second, which you can use an FPS unlocker and get higher frame times, but by default it's maxed out at 60 frames per second. So basically all of these jobs are running 60 times every single second. And that, if you do the math for that, the frame time for each, assuming perfect 60 frames per second, it does vary slightly, is approximately 16 milliseconds every single frame, which it's like, that's really fast. But so I made a diagram. Yeah, so this is what a frame might look like for jobs that are running in serial or synchronously. So, for example, this first process could be the rendering job. The middle one could be like physics calculations, and maybe the last one is just some other calculations. And you can see I labeled 60 frames per second, and then I just added a couple of timestamps, so 0 milliseconds, 9, 12, and then 16. So to understand defer, you have to understand that different code is running at different times in the frame. So like this first this first block of code for the rendering is happening at the start of the frame, just like for this example, it's starting at the start of the frame. And then this middle one, I just arbitrarily chose 9 milliseconds for it to start at, and so on. So what defer does is you can think of these starting points as, or these timestamps as resumption points, is what I like to call them, and I believe they're called that as well. So let's say that you call task.defer at the same time that the rendering code is happening. So you call it somewhere within the first block of code. Task.defer is going to create a new coroutine, and it's going to run it at the next resumption point within the frame. So it's, in this specific example, it's, if you called task.defer in the first block, it's gonna create the coroutine, but it's gonna run the coroutine in this second, or starting at this second block, somewhere in the second block. So that's kind of interesting, because let's say you wanted to run some code, but you didn't want it to run like within like basically at the same, sorry, you didn't want it to run like immediately, basically. So what this Roblox example is showing is that task.spawn is going to run immediately. Task.defer is going to run at the next resumption point. So I hope this diagram helps. But yeah. So that's pretty cool. And there's also one more example I can show you. There is task.delay. It takes a first argument as a number in seconds. And this one's a little more self-explanatory. So it's going to create a new coroutine, and it's going to run it after 1 second. So we go ahead and run this. Spawn defer after 1 second, it prints delay. So these are the 3 ways that you can create coroutines and either start the execution or resume the execution of them. And of course, we've also been using the task.wait function, where you can just yield the thread or the coroutine that it's called inside of for X amount of seconds. And also, an important thing to note is, if we go back to our diagram, so this is related to task.wait. So this heartbeat at the bottom of the at the bottom of the image, this is where scripts are initially ran by default. So, for example, this server script that I'm running here, this code is initially ran when the heartbeat phase is happening. And that applies to all scripts. That applies to all scripts. And another thing is, if I don't know, I don't think it picks up on the recording, but I'm going to read the little tooltip that pops up with task.wait. It says, it yields the current thread until the next heartbeat in which the given duration in seconds has passed. So basically what that's saying is, for example, if I pass 3 here, it's going to wait 3 seconds. And if I go back to my diagram, So we have task.wait 3 seconds. Let's just call this last section of this diagram, let's just call it the heartbeat step, for example. Task.wait 3 is every single frame, it's going to check on the heartbeat, has 3 seconds passed. If not, go to the next frame. It has 3 seconds passed. If not, go to the next frame. And then keep going to the next frame until 3 seconds has passed. And once it has, like, passed, then the coroutine manager is going to say, all right, now I'm going to resume this thread because 3 seconds has passed. So that's pretty cool. And the same actually applies to task.delay. It's going to resume on the during the heartbeat phase of the frame time after X amount of seconds has passed. Yeah. So let me just make sure I haven't missed anything. Yep, nope. Well, okay, so there's actually the last two functions I want to go over is task.cancel, and the equivalent coroutine version of that is coroutine.close. So just for an example, I'm gonna create a new thread. I'm gonna use task.spawn here. So function, and let's just say I'm gonna wait like 10 seconds. So let's say, for example, after 3 seconds. Let's say after 3 seconds, we don't want this process to run anymore. So it's going to time out after 3 seconds. And I intentionally put task.wait 10 in here for the example to show. So if we want to time out or cancel the thread from executing, we can simply just call task.cancel, and then we pass the thread reference. And so if I run this, oh, so let me also print cancel. All right, so now if I run this, see, it doesn't print anything. After 3 seconds, it prints canceled. If I were to wait here for 10 seconds, I'm gonna watch the time down here. Yep, should have ran by now, but it didn't because we canceled it. And now, you know, if I remove this, or I guess, so if I just decrease the time it waited inside the function body to 1 second, and I still had this this cancel down here. Let me see what happens here. Yeah, so process ran, and it actually prints canceled even though the process ran, which is pretty weird, like how it wouldn't throw an error there. But you can also check to see. So let's use some older functions we learned about. So I can make an if statement here. If coroutine.status past the thread reference is not equal to dead. So if the coroutine has not finished executing it, then I want to cancel it. And I'm just going to add like a warn down here. Okay. So, you know, print process ran, and it prints done. And it never prints canceled because the status was dead. So this condition fails. So, you know, there's some cool things you could do with it. And of course, this, so if I were to make this 5 seconds again, and I use task.cancel here, I could also use coroutine.close past the thread reference. And then if I try to run this, it's going to print canceled, done. It's been about 5 seconds now. It should have ran, it didn't because we canceled it. but we use coroutine.close this time. Yeah, so yeah, that pretty much wraps up what I wanted to go over in this video. Uh, yeah, uh, thanks for watching. If you liked it, hit that like button, subscribe, all that, and yeah.